Hello everyone, and welcome to the NEATEC Electronics Series. This video is about state machines, so let's get started. Alright everyone, welcome back. And we're going to continue our discussion on state machines. Now, if you recall, there were two types of state machines. You had a Moore machine and a Mealy machine. We talked about that in the last video. So the Moore machine was just based on sequence, right? And that's pretty much the example we went through in the last video. The Mealy machine also requires logic to determine which state it progresses to, okay? So let's look at this, right? In this, by the way, what is this? This is a state diagram, right? I just drew it for you, okay? Now, this initial state up here at the top has a name of start and a value. The state variable has a value of zero. Then it progresses to continue the next state and has a value of 1, and then continues back, right? Pretty straightforward, right? You can't get more simple than that. This is only one flip-flop, right? It has only one variable Q0, right? It's either going to be a 0 or a 1, right? All right. So let's make it a little more complicated. I know you want to do that, right? So suppose we're going to add an input 1. We're going to have a slash. That's a delimiter. We're going to call it a delimiter. I'm drawing the legend right now, and I'll talk more about it. Then we'll have an output. Say this is going to be called out 1, and this will be called out 2. All right. Now, this is called the legend. For many textbooks you look at, they may use this type of legend, but they don't have to. They need to separate the inputs from the outputs, and how they do it is up to the author. Okay? So they may not use slashes, they may not use commas, they may use parentheses, who knows, okay? But for this example, this is what we're going to use. Now, let's start. Suppose you see this. What do you think that means right there? Well, I'll tell you what it means. If you are in the start state, okay, and you clock it, or I should say not you, but your circuit, obviously, and you clock it, if in 1, and this right here represents in 1, right? Right there. If in 1 is equal to 1, it's going to come right back to itself. So if you clock it, it's going to stay in the start state no matter how many times you clock it, as long as in 1 is equal to 1. In addition to that, out 1 output right here, and out 2 right here, they're both going to output the value of 0 every time it's clocked. Okay? That's what that's saying. Now, for this transition, suppose we draw what do you think that means? Well, this means if you're in the start state and in 1 is 0, then it's going to make this transition to continue. Get it? In addition to that, it's going to output out 1 to be a 1 and out 2 to be a 0. Okay? Now, what about this? What do you think that means? Well, the X obviously means it doesn't matter if your in1, your input, is a 0 or a 1. Remember the I don't care state from your Karnaugh maps? It's the same thing. It doesn't matter if it's a 0 or a 1. It's going to take this transition from continue to start when it's clocked. In addition to that, out 1 will output a 0 and out 2 will output a 1. All right? This is called, on the right side, this is called a conditional transition, right? Because it's conditioned on the value of in1, it has to be 0. Now, on the other side, this is not called a conditional. Basically, this is called an unconditional transition. Get it? Because it doesn't matter what in1 is, it's going to take the transition. Now, let me state some things right now. If this legend, I'm going to write it up here, that's what that is. Whenever you read a map, they have a legend to give you the meanings of symbols and things like that. If this legend was, suppose you had in1, in2, in3, and then you had out 1, out 2, I don't know, you could keep on going to however much you want, right? You can see, all right, that instead of just having one value, you would have two other values to contend with, right? So it's only going to take this transition if all these input values are what they should be, right? And then it's obviously going to output. Here we just have two outputs. You could have as many outputs as you want, right? You could have as many inputs as you want. But to keep it simple, we're just using one input and two outputs right now. But the concepts are all the same, right? If all of these inputs were X's, that would be an unconditional transition. It wouldn't matter. It would make that transition, right? However, if they're not and they have to be a specific value for that transition, then you have something more interesting to work with, okay? All right, so let me just get rid of this. I wanted to make sure everyone understood that. So, let's think about this some more. We drew a state diagram right there, didn't we? Now let's draw a state table, shall we? So let me move this a little bit. Let me take your legend. I'm going to move that right up here on the top, okay? Now let me take this here. It's not going to fit, is it? I'll leave it right there. How's that? I'm going to get rid of these names just to make sure that we can get as much space as we can, okay? All right, here we go. There we go. Now, if we're going to draw a state table for this, okay, let's think about it. We have our present state, right? And we also have an input, right? In1, don't we? those are the two things that are going to determine when it makes the transition. So then what we're going to what we're going to do is go to the next state, right? Transition to the next state. Right? And for each transition, you have an output to contend, two outputs to contend with, right? So you're going to have out 1 and out 2. Okay? So remember, think of it that your present and your input, that's going to be a driving factor. I'm going to put a line there. I'm going to put a line here too. So let's draw it, right? Suppose your present state is 0. Remember, this has to go in normal. When I say normal, the binary order of 0, 1, 2, 3, 4, 5 if it was decimal, right? The equivalent. So 0, 0, if you're at 0, 0 and you clock it, input's 0 and you're at 0. So you're looking at this value right here. Can you see that right there? It's this value right here and this value right here. They're both 0. You clock it. You're going to go to what? You're going to go to 1, aren't you? Okay. Now, what's your output going to be? Output 1 is going to be a 1, right? Right here is your 1. Your output 2 is going to be a 0. Get it? Now, you know what? I'm going to just keep doing this. I think this would be a good way to get it across. So what's the next transit? What's the next one? It comes as 1, 0, right? Remember, if I was writing decimal here, that stands for decimal. This would be 0, this would be 1, this would be 2, and this would be 3. And I'm talking about the value of here to here. That's 0, 0. This is 1, 0. We're going to have 0, 1, and 1, 1. That's 1, 2, 0, 1, 2, 3 in binary, okay? So, let's keep going here. So, present state is 0. We're right over here again, right? In is 1. That means we're up here. If you clock it, what's your next state? Next state is going to be what? Stays at 0, doesn't it? And what are your outputs? Right? Now, let's do the next one, okay? You are in state 1. Your present state is in state 1. It's in continue, right? And in 1 is 0. And you're looking over here, right? And remember that X, it doesn't matter, does it? If it's 0 or 1. But right now you're in 0. That means your out 1 is going to be a 0. Well, your next state is going to be, 0. Your out 1 is going to be a 0, and your out 2 is going to be a 1. You guys got that? 3, you're still in continue. Your in 1 is a 1. It's going to be the same thing, remember? It doesn't matter. This is an X there. If it's a 0 or if it's a 1. Okay, if you're in that state, doesn't matter what your in 1 is anyway. It's going to be the same. So it's going to be 0, 0, 1. You guys get that? Now remember, when we write our state tables, we're missing something here, aren't we? So for this example, let's use a JK flip-flop instead of a D flip-flop, okay? So let's do this, shall we? I'm going to get rid of this column. We don't need that. I'm going to take this. I'm going to move it over here. why don't I just add it on the right? It'd probably be easier that way. So with your JK flip-flop, you have one JK flip-flop. You have to have your sync inputs, right? J and K. So let's look at the output, right? So you're going from a present state of, I'm going to make this blue, okay? Your present state is 0, and you're going, your next state is a 1. So Q goes from a 0 to 1. If you recall, I'm going to just keep it blue, okay? It'd probably be easier than switching. That will be a 1x. Remember, you can either toggle it. If they're both high, it's going to toggle. So it could toggle to 1, or you could set it, all right, which would be a 1, 0. Either way, K, it doesn't matter. J has to be a 1. Now here we're staying, the next one, if we look at the next one right here, you're going from a 0 to a 0 transition, okay? That's going to be 0x, right? It's either the no change, right? It's no change, or you're going to reset it, okay? If you have any questions on this, I would suggest you go to the video, review the video on flip-flops, okay? So the next one, you're going from a state 1, right? That's what Q is, 1, and you're going to a 0 right here, okay? 1 to 0. So you can either toggle it or reset it, right? It's going to be x1. And finally, you're going from a 1 to a 0. It's the same thing, isn't it? It's going to be an x1. All right, you guys. There you go. That is your table. Okay? Now, once you have the state table, what do you think the next thing to do is? If you said Karnaugh maps, you're right, okay? So for this, I'm going to have to get more space. I'll see you in a minute. All right, everyone. So I drew 4 Karnaugh maps below the state table right here, okay? Now, remember, you had a present right here, you have your input 1, and you have your next state right here. Obviously, those don't require Karnaugh maps, those are your inputs, but you need to have a Karnaugh map because you need a circuit for your output 1, and output 2, right, for each of your outputs. If there were more outputs, you need a Karnaugh map for each of them. And you need a Karnaugh map for your J and your K. Now, if you decided to use a D flip-flop, you wouldn't need to have 2 Karnaugh maps, one for J and for K. You could just have one for D. But since you're so excited about this, let's just do the JK, right? Why not? Have some fun with it a little bit, right? So I'm going to go through this rather quickly. If you have any questions on grouping and Karnaugh maps, I would encourage you to watch the video on Karnaugh maps. But let's just go through each of these right now. This one, 1, 0, x, right? Remember, you're using your present state and your end state, right? So if Q is 0, when I say present, this is your Q. I'll put Q there for you. That's Q, right? And that corresponds to your state values right here. That's Q, okay? Q is 0, and there's your in1, right? So you have 0, 0. If you come over here for J, which is in this column right here, see you have a 1 and a 0. Here's your 1 and 0. And the last two are XX, right? For the K, which is right here, if you just look at it, it's going to be what? XX. What do you think the next one's going to be? Well, it's 1s, right? 1, 1. You can't go wrong there. Got it? And we do the same things for the out 1 and the out 2. Okay? So out 1 is going to be 1, 0. 0, 0. And the out 2 is going to be 0, 0, 1, 1. Alright? Now, the next thing we want to do is group. Okay? So, if I was grouping this one, remember an X can be either a 0 or a 1, right? So I would group it this way. Right? This one would make the x's both equal to 1. That would group them like that. This one you can't do anything, so you have 1 here, and this one pretty much group them like that, right? So now let's get the expressions, right? I'm going to write the expressions above here, right? So this one, J, is going to equal, well, it's pretty straightforward. It's going to be in1 bar, because it's a 0, right? Okay. This one, K, is going to equal 1, because they're all 1s, right? You can group them in, make the two x's 1s, it's all 1s, so that means K is equal to 1, right? Out 1, well, that's going to be out 1 equals, that's going to be equal to Q R dot in1 bar. It's a 1. There's no, it's a 1, okay? In1 bar, right? And this one right here, out 2, that's going to equal, well, it looks like it's just going to equal Q, doesn't it? Okay? So there you have it, right? There is your karnaugh maps right there. So let's do this, shall we? Let's start making the circuit. Alright, now what do you have with these kind of circuits? You have a J, you have a K, you have a clock here, right? And you have a Q. And you have a Q bar, right? You have a set and preset, but I'm not going to draw those things, right? So as usual, I'm just going to take a red wire, and that's your clock. Got it? Now, what is your J equal to? We're going to have two inputs here, obviously. I didn't put them there. We're going to have one input, I'm sorry, in 1, right? And we have two outputs, right? So your in 1, whatever it is, bring it in. So J is equal to in 1 bar, so we're going to go through an inverter here, aren't we? Let's take it, and then we'll go into J. Got it? Okay. K is always 1, isn't it? So that can go to plus VCC. Okay? Your plus 5 volts. Okay? Now, your output, here's your Q, it's coming out. Right? This is your out 2, isn't it? Because out 2 is equal to Q, right? Now what's out 1 equal to? Out 1 is equal to Q bar, which is this one. Make use of it. And we're going to end it with N1 bar. Alright, so I'm going to have to take it this way. How's the best way to get over there? This may not be as pretty as I had hoped. So it's N1 bar here and Q bar here. And they'll come out like this. And then we got to AND them, right? Because it's an AND gate, right? We're going to AND them. And this is going to be your out 1. Get it? After you do these for a bit, they become pretty straightforward. As you can see, the thing you really have to watch out for when you do these is you have to take your time when you make your state table and state diagrams. Take your time and do them very accurately. Then when you do that, then you have to make your karnaugh maps, right? Obviously. Take your time when making your karnaugh maps. It's very easy, because we're all human, for you to take a value and put it in the wrong cell. I mean, you could just have a momentary lapse of reason and it's in the wrong cell, and that's all it takes. And then everything else you do after that is going to result in the circuit not being correct. Okay, so once you do it, I suggest take a quick break, stand up, have a cup of coffee or tea or whatever you like to drink. Well, no, coffee or tea or water, and then sit back down and then check your work. Okay, and then once you're sure of that, then move on to the next step. In other words, for every step, double check yourself. Okay, because it's a real drag if you get all the way to the end and you realize you made a dumb mistake in the beginning and you got to do the whole thing over. Okay, now you should, obviously, since we had one state there, we're going between 0 and 1. I mean, you only needed one flip-flop. This circuit was easy. I mean, if you were going with 3, 4, 5 flip-flops, it would be a lot more complicated, right? You may have to use software to help you because it would get too cumbersome. But you understand the basics now of what a state machine is, right? I hope this has been helpful to you, and enjoy your study of digital electronics. Bye now.